In section 7.4, we're going to be looking at some special right triangles. The reason they're special right triangles is because they have some nice, easy-to-use shortcuts for finding their side lengths. These two right triangles, a 45-45-90 right triangle and a 30-60-90 right triangle, you only need to know one side length and you can find all three sides, which is really convenient. So starting out with a 45-45-90, we have obviously a 90-degree angle because it is a right triangle. And if these other two angles, the acute angles, are both 45 degrees, it's actually an interesting triangle in itself. Because of the fact that we have two congruent angles, we also have two congruent sides. Remember, that makes it an isosceles triangle. In this case, the legs of that right triangle are congruent, and we're going to talk about some shortcuts to find all the sides here. The 30-60-90 is our other special right triangle. Of course, we have a right angle here, and the two acute angles would be 30 degrees and 60 degrees. And we're going to talk about a shortcut to find all of these sides as well. So we're going to start first with the 45-45-90 and talk about what we know. First of all, how do side lengths and angle measures relate in an isosceles right triangle? And that kind of is the key term. Whether you know it's a 45-45-90 or whether you know it's an isosceles right triangle, well, isosceles triangle is two congruent sides, and if it's a right triangle, the two congruent sides would have to be the legs. And marking those congruent would mean the base angles have to be congruent. So if we already have a 90-degree angle, and the angles add up to 180, we have 90 degrees left for those two angles, so 90 divided by 2, it makes these angles have to each be 45 degrees. Because they are congruent angles in that isosceles triangle. They are the base angles. So going even further, if I called this side x, well then this side is congruent, right? So that would also have to be x. What's the length of the, in this case, the hypotenuse? Well, the fact that these two sides are the same, I'm calling them x right now, couldn't I use Pythagorean theorem with the two legs squared added together would equal the hypotenuse squared? So I'm going to take one leg, which is x, and square it, plus the other leg, which is also x, and square it, because I know that leg squared plus leg squared equals hypotenuse squared. I'm just going to call this h for hypotenuse, seeing I don't know that yet, but hypotenuse squared. Now, in this case, I can combine these like terms. X squared plus x squared is a total of 2x squareds. And that equals whatever the hypotenuse is squared. Again, just using Pythagorean theorem. What I'm trying to do is figure out what could I call h relative to x, because then knowing these sides would mean I would know the hypotenuse. And the only step I have to do yet is undo squared on the hypotenuse there by taking square root of both sides here. So what does h equal? I have square root of 2x squared. Now, if you remember simplifying square roots, if we can take the square root of either of these things being multiplied in here, then we can take that out. Well, I don't know the square root of 2. It's an irrational, non-perfect square there, but I do know the square root of x squared. The square root of x squared is x. So it looks like the hypotenuse is actually x outside of the square root times the square root of just 2 inside. This can be an expression then for the hypotenuse instead of calling it just h for hypotenuse. Sorry, I don't know why I had that squared on there. Instead of just calling it h, well, if these are x, it looks like the hypotenuse is just whatever this side length is, whatever that x is, times square root of 2. So if you knew the legs that were both 5, let's say the legs were 5, well, then the hypotenuse would be 5 times square root of 2. And if the legs were 7, then the hypotenuse would be 7 square root of 2. So just like that, knowing the legs means you can find the hypotenuse. Well, if all we're doing, if we have the legs to get the hypotenuse, is just multiplying by square root of 2, right? It's just x times square root of 2. How would you go backwards then if I knew the hypotenuse and I needed these leg lengths? Well, instead of multiplying by square root of 2, what's the opposite of multiplying? Divide by square root of 2. And so on your summary sheet that you should have, you can jot this down. But it's really nice. So either you have the legs or you have the hypotenuse, and you can find one or the other. If you have the legs, multiply by square root of 2 to get the hypotenuse, and then 45-45-90. if you have the hypotenuse, divide by square root of 2 to get back to the legs. I think the picture is probably enough info. If you want in words in the actual theorem here for a 45, 45, 90 right triangle, they're saying in an isosceles right triangle, which is what a 45, 45, 90 is, right? It's an isosceles right triangle. The hypotenuse is just square root of 2 times as long as each of those legs. So you can write that theorem down if you want. Let's try some examples here. Find all the missing side lengths in all of these triangles. If you notice here, I have the right angle given. Oh, yawning here. And I have a 45-degree angle. Well, doesn't this have to be 45 degrees as well then to add up to 180? So this is a 45, 45 right triangle, which means that the legs are congruent. It's isosceles. This leg is also 12. And now to get the hypotenuse, I know I just take the legs times square root of 2. Therefore, the hypotenuse is 12 times square root of 2. Just like that, I know all of the side lengths. All right, what about in this triangle here? It is a right triangle. Oh, okay, notice both of these sides are 10 square root of 2, which means if these are congruent sides, then it's an isosceles triangle, has congruent base angles, and these have to be 45 degrees. So it is a 45, 45, 90. Now the legs are 10 square root of 2. To get the hypotenuse, I'm supposed to multiply by square root of 2. So I'm actually taking the 10 square root of 2 sides, but remember how I had to multiply by square root of 2 to get the hypotenuse? So I still have to multiply by square root of 2. Now you might be thinking, well, this is like 10 times square root of 4, because maybe you're thinking, I know when I multiply square roots, I multiply those numbers together. 2 times 2 is 4, and now I'm doing square root of 4. Or maybe you were thinking square root of 2 times square root of 2. That's like square root of 2 squared, and the square root and square cancel. That should be just 2. So maybe you were thinking that that's times 2 right away, or maybe if you did this step, you know the square root of 4 is 2. So either way, it's 10 times 2. And 10 times 2, the hypotenuse in this case, is 20. So there you go. Starting with the legs, you can get the hypotenuse by multiplying by square root of 2 in a 45, 45, 90. What about in this triangle? Is it a 45, 45, 90? Well, it is a right triangle. I have 2 congruent angles. Oh yeah, so those both have to be 45-degree angles then. So this is a 45, 45, 90, which means I know that those legs are congruent. Oh, in this case, I have the hypotenuse. To go backwards and get the legs, I actually need to divide by square root of 2, remember? Because I was multiplying by square root of 2 when I had the legs to get hypotenuse. Now I have hypotenuse, so I'm going to divide by square root of 2 to go backwards. Be careful here. When I'm doing 8 and dividing by square root of 2, I know I can never leave square root in the denominator. The way to get rid of that square root in the denominator is multiply by square root of 2 on top and bottom. This is like multiplying by 1, so that's why it's okay. Here on top, I get 8 times square root of 2. On bottom, I did this so that square root of 2 times square root of 2 is just 2. As we saw here, square root of 2 times square root of 2 is just 2, because it's like square root of 4 or 2. And finally, 8 divided by 2 is 4. So it's actually 4 square root of 2. When I simplify, now that's the length of both legs in this case. So there we go. We found the legs and the hypotenuse of this 45, 45, 90. And let's do another example here. Is this a 45, 45, 90 right triangle? It should be, right? I have a right angle. 2 congruent sides also means 2 congruent angles. It's isosceles. Legs are congruent. Those are 45-degree angles then. All right, 15 square root of 2 is the hypotenuse. To get the legs, you need to divide by that square root of 2. Remember, you multiply by square root of 2 to get the hypotenuse. Divide by square root of 2 to get back to the legs. In this case, really, it's like the square root of 2 just cancels. That must have meant that the legs were both 15. Because if you notice, if these were 15, you would just multiply by square root of 2 and get your hypotenuse there. So we're all set. So some practice with 45, 45, 90s right triangle. 45, 45, 90 right triangles. This is our first special right triangle, and we're going to look at our second special right triangle here and figure out what is the relationship between the sides in a 30, 60, 90 right triangle. But first, we actually start with an equilateral triangle. And you're always going to picture an equilateral triangle when you do 30, 60, 90 right triangles and their shortcuts. What I'm going to do here, what are the angle measures, first of all, in an equilateral triangle? Remember, if we have congruent sides, we also have congruent angles, so 180 divided by 3. Each of these angles measures 60 degrees. And this is helpful because the next thing I'm going to do is actually draw an altitude in this triangle from one vertex. Now, an altitude goes from that vertex to the opposite side at a right angle, or perpendicular to the opposite side. Mark my right angle here. But now you notice I have two right triangles that are formed, and an altitude of an isosceles or equilateral triangle also is an angle bisector. Therefore, I've split this 60-degree angle in half. So each of these angle measures is 30 degrees. And you notice now I'm looking at this 30, 60, 90 right triangle that I said was our next special right triangle. So I'm going to highlight the triangle we're focusing on, remembering that it did come from this original equilateral triangle. And the first question that we can do that relates two sides very easily is, how does the short leg of this right triangle, meaning here would be my shorter leg, how does that compare to the side of the actual original equilateral triangle? Think about it this way. If you knew that this was x, whatever that might be, 5, let's say this is 5, a length of 5. Well, didn't this altitude also act as a median because it was an equilateral triangle? Therefore, I've split this side in half. Again, let's say this is 5, then this whole side was 10. It was really just whatever this is times 2, right? So if this is x, this whole side would be 2x, twice times x. Well, then it was an equilateral triangle, wasn't it? So if this side is 2x, so is this side. And this side. So this side is twice the length of the short leg. The hypotenuse of the right triangle, which was an original side of the triangle, is twice the length of the short leg of this right triangle, seeing that this was half of the original side of my equilateral. So if this is 5, this is 10, and if this is 7, this is 14. My question is, what is the altitude, what is this height, or what is this longer leg? So I'm going to solve for this and find a relationship using Pythagorean theorem. I have these two legs, this hypotenuse, and I want to find what would this leg length be. So a is one leg, so a squared plus the other leg, which is x squared, equals the hypotenuse, which is 2x. Quantity has to be squared. Remember to square both of these. Oops. So now I have a squared plus x squared equals, I have to square 2 and get 4 and also square x. Now I'm trying to solve for a and get a alone, so I'm going to subtract x squared from both sides here. So I have a squared equals 4x squared minus 1x squared would be 3x squareds. And I'm almost there, because I just take square root, because it was squared to get a alone. It looks like a is equal to the square root of 3x squared. And just like before, I can take square root of any parts, and I notice, well, I don't know the square root of 3, but I do know the square root of x squared. The square root of x squared is x. Therefore, it looks like that side A, which is the height of the original equilateral, which is the long leg of this 30, 60, 90, is an x outside times the square root of 3. Remember how it was x times square root of 2 for a 45, 45, 90? This is x times square root of 3 in a 30, 60, 90 for that long leg, which was the altitude of the height of the original triangle. So very cool. Again, if you know just one side in a 30, 60, 90, you can find all three. The short leg is kind of your most important side, because once you have that, you can find the others very easily. So I'll put some stars here and do that on your shortcut sheet. Because if you have this short leg, to get the hypotenuse, all you do is times by 2. But to go backwards, if you're trying to get back to the short leg, you'd have to divide by 2, of course, because that would undo it. If you knew this was 20 divided by 2, this side is 10. If you have the short leg, you can easily get the long leg. All you have to do is times by square root of 3. If you have the long leg and you need to go back to the short leg, do the opposite of multiplying by square root of 3 and divide by square root of 3. Let's say I knew this was 5, then this would be 5 times square root of 3. And if you knew this was 5 square root of 3, you would divide by square root of 3 or cancel it out to get back to 5. So the summary in words for a 30, 60, 90, and I don't know that you need to write this, I think the picture does enough, but in a 30, 60, 90 right triangle, the hypotenuse is twice the length of the short leg, and this longer leg is square root of 3 times the shorter leg. So we're going to use these shortcuts to do some examples here. Let's find all the missing side lengths in these 30, 60, 90 right triangles. I know this is a 30, 60, 90. Here I have 30 and 90. The remaining angle has to be 60. I have a 60 and a 90. The remaining angle has to be 30. So these are all 30, 60, 90 right triangles to start. Now remember the relationships here. In a 30, 60, 90, and I'm drawing this the other way. Notice I have the triangle going this way, but we should realize the short leg is the most important. That's x. The hypotenuse, remember to always visualize. I always visualize that it came from a original equilateral triangle because it helps me to see that this side, this would have been an original from the equilateral, so this would be double that, or 2x, and this long leg is x times square root of 3. Let's use that to solve this one first. Actually, this might be our trickiest one. Because if you notice, 15 is actually the length of the longer leg. And first, I want to go back to the short leg. That's always the first one you find if you don't have it. Now, if you have the long leg and you're going back to short leg, since you would go times square root of 3 to get long leg, we undo that by dividing by square root of 3. So here, I need to take 15 and divide by square root of 3, which of course you can't leave it that way. Cannot leave a radical in the denominator, so I'm going to multiply by square root of 3 over square root of 3, which is like multiplying by 1. I get 15 square root of 3 on top. On bottom, square root of 3 times square root of 3, of course, is just 3. And then I can do 15 divided by 3 and get 5 times that square root of 3. So the short leg is 5 square root of 3. Makes sense because if I had multiplied this by square root of 3, I would get 5 times 3 or 15. And now, short leg to hypotenuse is what I'm doing right here. Remember that the hypotenuse is double that because you can picture that equilateral triangle. And this would have been half of the original side, which this was an original side, so times by 2. Now 5 square root of 3 times 2, you're just going to multiply the numbers because you're doing 5 times 2, so this is actually 10 times square root of 3. And now we found all of the side lengths of my 30, 60, 90 here. Alright. Let's try this one here. Oh man, it looks like once again I am given the long leg of this 30, 60, 90. Here's my short leg. Here's my hypotenuse. So again, this is long leg, which would have been the short leg times square root of 3, because short leg gets the original x. So to go backwards from long leg to short leg, I have to divide by that square root of 3 or get rid of that square root of 3. Works out a lot nicer here though, because the long leg was 4 square root of 3, so dividing by square root of 3 just makes that cancel. Short leg was 4. Notice, pretty simple to see that from the short leg of 4 times square root of 3 would be 4 square root of 3, so that looks good. From short leg to hypotenuse, remember the original equilateral triangle would have come out this way. So 4 would have been half of that side. The whole side would have been 8, or double that, right, times 2. So 4 times 2 is 8 for hypotenuse. Alright. In this 30, 60, 90, hey, we're finally given the short leg. Square root of 3 is the short leg. This is the easiest one to find the other two sides. I know that from short leg to hypotenuse, this happens to be the same orientation, I multiply by 2. So square root of 3 times 2 would just be 2 square root of 3. Because remember that equilateral triangle, if you picture it, would go out this way, and this side would have been double square root of 3, or 2 square roots of 3. The long leg, you take the short leg times square root of 3. So I'm actually taking the short leg of square root of 3 times another square root of 3. Well, square root of 3 times square root of 3 is just 3, because it's square root of 9, which is 3. So working with some 30, 60, 90 special right triangles, looking at short leg being kind of that most important side, the one you want first if you don't have it. Multiply by square root of 3 to get long leg. Multiply by 2 to get hypotenuse. If you have the hypotenuse, divide by 2 to get the short leg. We didn't have an example yet that you had the hypotenuse. If you have the long leg, divide by square root of 3 to get the short leg. All right. Of course, this is your summary sheet that you should have. Quick reminder, in a 45, 45, 90, two congruent angles and two congruent sides goes together. It's an isosceles right triangle. So these sides can both be called x because they are congruent legs. Hypotenuse is whatever that side length or leg length was times square root of 2. Oh, the way I remember that this one's square root of 2 is because it has two congruent angles, two congruent sides. So that helps me remember that a 45, 45, 90 is x times square root of 2 for the hypotenuse. In a 30, 60, 90, remember the short leg is your most important one. To get the hypotenuse, you're going to multiply by square root of 2. If you have the hypotenuse and you need back to short leg, you're going to divide by 2. I'm sorry that I said square root there. Multiply by 2 or divide by 2. If you have the short leg and you need the long leg of a 30, 60, 90, you're going to multiply by square root of 3. If you have the long leg, you're going back to short leg, you're going to divide by square root of 3. And the way I remember that this is square root of 3, a few ways. You can say, well, there's a 30-degree angle, so the 3 shows up there. Or there's 3 different sides, 3 different angles. That helps remember that in a 30, 60, 90, it's the square root of 3. Oh, and over here, I should have shown that if you have the legs, you multiply by square root of 2 to get that hypotenuse. If you have the hypotenuse and you need the legs, you're going to divide by square root of 2. Let's summarize these all on this slide. It's kind of neat, actually. We're picturing we're flying a kite. A kite is attached to a 100-foot string. How far above the ground is the kite when the string forms the given angle with the ground? Okay, so let's say I'm flying my kite, and first it makes a 30-degree angle with the ground. So not that big of an angle. So my kite is up here, and the angle with the ground is 30 degrees. Question is, how far above the ground is my kite? So I need, that's a great vertical line. I need this distance here. I'll call it y. Now keep in mind this is a right triangle because if I'm measuring the distance from the ground, I'm going at a right angle. I'm doing a height there. Oh, and the thing I knew is that we had a 100-foot string on my kite, so this is 100 feet. Now this example I want you to do for tomorrow, this is a 30, 60, 90 right triangle. 100 is the hypotenuse of that 30, 60, 90. You're finding short leg. Do that for tomorrow. Now it looks like the kite's making a 45-degree angle with the ground. Now it's a little bit higher up here. The kite string is still 100 feet, but I'm forming an angle of 45 degrees with the ground. I want this height, call this z. It is a right triangle. This one is a 45, 45, 90 right triangle. I have the hypotenuse. I need this leg, which would also be the same as this leg. Again, do this one for tomorrow. And then, now my kite is at a 60-degree angle with the ground, so even greater height there. Still a 100-foot string. And here's me flying it. 60-degree angle with the ground. How high is the kite off of the ground now? My height should steadily increase here. Now I know you're going to get answers with square roots in them. And you can get a decimal here since I'm actually looking for height off the ground. I'll call this A. Now I want you to do this one for tomorrow as well. Notice it is a 30, 60, 90 right triangle. I have the hypotenuse. You're going to have to find short leg first, then long leg. And we'll check these answers tomorrow in class. One more example here. The recycling logo is much like an equilateral triangle. It's based off of an equilateral triangle with side lengths of 6 inches. Let's see here. Let's see how close that was. Okay. So it's approximately an equilateral triangle. The side lengths are 6 inches. what's the logo's height? Oh, so I want this distance here. Well, actually, if you picture it, again, this was an equilateral triangle to start with. I'm just highlighting this triangle on the right here. The side length was 6 inches. I want to know the height, which is this. I'll call it h. Well, if the original triangle was here, all the angles were 60 degrees, it's equilateral. I've now split that angle, 30 degrees. Remember that our 30, 60, 90 came from that equilateral triangle. It's half of that equilateral triangle when you draw a height. And now I should be able to find that height. Keep in mind here, the 6 inches is my hypotenuse. And the first thing you do is actually get back to your short leg. And the way you do that is realizing, well, if this was 6 inches, so was this entire length. But I've now split that. So this distance would be half of 6 inches, or 3 inches. Remember, you divide by 2 from hypotenuse to short leg. And now, from short leg to long leg, you should remember that you multiply by a square root, in this case square root of 3, remembering there's 3 different sides, 3 different angles, or a 30-degree angle, so therefore the height is the 3 inches of the short leg times square root of 3. And this would also be in inches, like all the other measurements in this case. You know what though, since it is a real-life problem, it might be nice to get an actual decimal answer, just because it is real life, so I'd like to know what 3 square root of 3 is. I'm going to put that in the calculator. And I'm getting approximately, because I know this is going to be rounded here, it's 5.196, so actually 5.20 accurate to do 2 decimal places. And there we have it. So today, working with 30, 60, 90 and 45, 45, 90 special right triangles, and make sure you have that kite example done for tomorrow.